Control. So today I'm going to be talking about service assurance across combined physical and virtual networks. Everybody's talking a lot about virtualization and everyone's very excited about it. If you can't, but there are two key themes here. Number one is that for a very long time services are going to cross a combined physical and virtual network. And so obviously the orchestration required includes both. And secondly, that if you can't assure the services that you're going through all this wonderful automated turn-up, then you're not going to be able to sell them. So the real focus today is on this service assurance. So I'm going to go through three different sections here. The first is just problem overview. Talk about the challenges of assurance across the combined networks. Then I'm going to go through a very straightforward 5-step solution to this problem taken from the world of modern software. And the solution is tangible, real, feasible, implemented in some tier 1 operators worldwide. So nothing I'm going to be presenting there is magic. It's all feasible in terms of what's happening. And then finally, I'm going to just talk about the industry context where this fits in terms of standards and discussions. So today's physical networks. Down at the bottom, I've got this network here. And the reality of telecom, the physical networks today, so this is just today, this is just physical networks, no virtualization involved. I look down at the bottom, that network has multiple different domains. I've got an MPLS core domain over here. I've got third-party access vendors. I've got radio segments. I've got an evolved packet core segment. And it doesn't matter if I'm doing a mobile example like this or I'm doing, and of course I got the RAN out here and that ultimately goes to the subscriber. Whether I'm talking about mobile examples or whether I'm talking about wireline examples, the current networks are multi-domain. There are many different networks. Typically all of them are engineered with different operational support systems, etc. They're all multi-layer. Even everybody talks about Ethernet backhaul. I haven't seen an Ethernet backhaul network that doesn't have at least 4 layers. They've got, some DWDM, they've got some Ethernet, they've got often have an MPLS implementation, and ultimately they're IP. So, and I've seen one with 7. So it's pretty amazing how complex these networks can be. They're multi-vendor. There's no case where it's one vendor end to end. And but I would say the good news is they're relatively well instrumented. What you find is that all the network elements have appropriate fault mechanisms. They're all collecting utilization information on the path of the service. And commonly, you'll find things like monitoring probes and stuff that, in this case, for example, is injecting synthetic test frames, Y1731 or TWAMP, that reflects off in order to measure delay variation, and frame loss on whatever the test path is. Now, some networks are better instrumented than others, but certainly there's been quite a move afoot to do that because you can't run this network if you can't measure it at all. Now, on top of that are a ton of systems. So there are inventory systems. This is incredibly simple. Multiple different inventory systems, fault management systems, element management systems, monitoring systems that are collecting stuff. Typically, there are actually, in a real world tier 1 operator, there are hundreds of systems. I had one tier 1 operator that had more than 200 in the wireless implementation alone. The other big problem in here is huge data quality issues. The accuracy of the information in any of the systems relative to what's actually in the network is often highly questionable. And very misaligned identifiers. A network element ID in the inventory system might not match what's configured in your network element in the actual such. So synthetically going across. So the challenge of what really happens when you operate this network, when you try to assure the services across this network, is you have a lot of people and a lot of spreadsheets. It's quite amazing how extensively Excel is used. I think it's the telecom industry's #1 OSS. So, it's not uncommon that average an hour or up to an hour just to sectionalize service troubles. When I lose connectivity from my core back here, how do I know where it is in the network? It basically sends a team of detectives to look at all your different systems. Questions: how hot should I run my network? At what utilization level will I start seeing delay variation, and frame loss that's actually going to impact the quality of service and impact my end customer experience? How can I hold my access vendors accountable if I'm measuring the performance? How can I gather all that data and actually determine whether they're meeting their SLA or not, force them into those access credits and force them through? what percentage of my budget should I give to these guys versus these guys, versus the RAN guys, etc.? Well, which of them is impacting the end user experience? And if I don't have the data to help me with that, I make guesses. And which regions are performing better? Why? These are just like a smattering of 4 interesting questions. But there are tons of them. And what happens is people go about gathering information, studying all these different systems, putting together the puzzle, and doing the best they can to figure out what's happening in today's physical networks. Now, of course, NFV is going to solve everything, right? So we're going to add in NFV. So there, I've added in NFV. So what's happening now is I have I'm still going to have all these physical implementations. No one's going to rip and replace this that takes place. I'm going to add in this case, a virtual EPC, but it could be a virtual data center that I'm going to add firewall services, et cetera, for enterprise as well. I'm still going to have faults coming up. I'm still going to have service OEM. In fact, I've actually got to make sure that I'm measuring the delay, deliberation, frame loss from my virtual components to my physical, et cetera. And I've got a whole bunch of new systems. I'm going to have certainly my OpenStack and or VMware, depending on my Vim layer. I'm going to have a VNFM, if not multiple, potentially per vendor. I'm going to have an NFV orchestrator, domain orchestrator, resource orchestrator, et cetera, that's underway. Ultimately, it's going to be more complex. There are more failure modes. It's more complex. There's a whole new section. And for those of you who have lived through the TDM to packet transition, you realize that even if the packet network were super simple and fully automated and such, the TDM, the operations guys didn't do better because they just had another domain and another technology that they actually had to go to. So, what's the solution to this? Taken from the world of modern software. So I thought I'd just step back. For those of you who remember 20 years ago, navigation systems, when you had to get from here to there, especially for those of us who travel a lot, there is a real world road down at the bottom. The systems were physical maps I had to have in place. I had to go find my maps that took place before this was all centralized and cloudified and such. I had to go figure out a path from here to there. I'd often mark it down, write down my directions, keep it going. If I ever got lost, I had a great fix, which I would go ask somebody for help. Often I'd listen to the radio to see if there was traffic on something, and is that 405 and Bank on my route as I'm driving along that take place. I don't even know about things like construction, etc. So there are really 5 Google Maps in 5 not so easy steps. Okay, so the first step that allows what Google, you think what that technology that's inside there, it's cool. It really is. And if you actually think about how it works, it's quite fascinating. So first of all, you've actually got a road system map. You actually have to map all of the different roads and where they are lat long, how they're connected, what you're allowed to do at every intersection. And that has to be a comprehensive road system map. It has to handle flyovers, it has to handle roundabouts, it has to handle one-way streets, it has to handle all kinds of things that you could experience in the real world. Okay? The great challenge was to actually produce that detailed information model, that is the path system of the roadmap, and then find the data sources that allow you to populate it and populate it accurately and keep it current. So that's challenge 1. That one alone is very, very hard. The second big step is to instrument. So you've actually got to figure out how fast it is on that segment of the 405, how that segment it is on the 101. If you guys can tell, I might be living in California right now. And so they have to instrument the network. So what things like Google does is, of course, all the smartphones are sitting there and they're traveling with you as they're going on that segment. And if you're running Google Maps, it's actually measuring the performance. There are a whole bunch of different ways of doing this. But ultimately, you've actually got to measure the performance, the speeds, the traffic levels that are taking place. And you actually have to gather that data in a central cloud. Then there is this really complex high scale. Think about the scale of this problem. right? In terms of how big we're talking about, run the centralized detailed analytics that that against that roadmap, these people, therefore these are actually the best route to take, or reroute these people around that accident that just happened, and then take action, which is to actually go through. So those are the 5 big steps that something like Google undertook. So now let's step back and think about what that looks like in terms of service assurance in a telecom network. So the first thing that has to happen is the same step, is I've got to do an information model. So I've actually got to know the path of I need to know an inventory of all my services that are being delivered to all of the customers. I have to know the path of that service through the physical infrastructure. I have to hold all that. And my model, like Google's that has to handle roundabouts and flyovers and one-way streets, my information model has to handle DWDM, it has to handle ATM, it has to handle Ethernet, it has to handle multi-point services, point-to-point services, all of the layers, models, etc. That's a hard problem to actually figure out how to model it, just as it was hard in the Google space. Fortunately, there's been a significant amount of industry work on this, and if you've actually looked at the ITU models, you've looked at the TMF-SID models, you look at the work that's going on at MEF and ONF in terms of information models, there's actually a pretty consistent theme throughout that, and it is a very generalized, relatively straightforward model that makes it possible to populate a detailed model of the network, and it has to be flexible enough to handle the variations in any particular service provider's network. So that's feasible, and this is the hardest problem, by the way. After you've created the model, the next thing you have to do is populate it. Okay, so I can now represent any network. Well, how do I know what your network looks like, what your list of services are, and how they traverse? That is the process that we've been implementing on that is to just map the data sources. There's no manual entry here. There can never be any manual entry here. So I might get most of my information through the config files from the network elements that allow me to go in and populate this. Unfortunately, that's important and it's trusted information. It's also insufficient, because if I go across this access vendor, for example, this network element, I can ask it all at once. It doesn't know that that access vendor is Verizon or what its circuit ID is. That information is unavailable, nor does it know what the address of this site is, nor does it know who the prime is, right? So there's typically a set of data sources that you have to suck from in order to populate the model. In addition, there needs to be an audit, because the information you'll get from here and from here often mismatch what's actually in the network. So you've actually got to clean this data up, because especially while the network can be trusted, the other stuff doesn't. And then finally, this process has to be continuous. You can't do it once. It has to be ongoing, that you're continually sucking this up, because services, networks change over time. So those are the first challenges. Doesn't mean so first step, again, not so easy, but it is actually the first step in the process. Second, the network needs to be adequately instrumented. As I said, in most cases, you'll find the network is actually relatively well instrumented, and there's tons and tons of data that this network's capable of generating. Typically the first problem is actually that you got all the data, you just don't know what to do with it. So after you've done that, the third step is, again, relatively straightforward, gathering the data. Typically, this data is being gathered in these systems already. It's just not being analyzed against a proper service model, so you understand the impact of all this data on the services. So you can often gather it from these systems as well, although sometimes it requires connections directly to the network element. Finally, big data analytics, same problem. This is a big scale system, just as the Google example was. So there's analytics to understand what the operational state of each of those services. Are they meeting their SLAs? Where are my traffic thing? All those sets of questions that I asked you, right? That at the very beginning need to be analyzed. And then finally, the last big step in the service assurance side is to, after you've essentially come up with a set of actionable actions that of the top things you need to do to ensure your services or improve your services, or ideally proactively prevent outages, for example, is to drive specific workflows actions you have to take in order to make sure you get proper quality assurance. And those actions then push down into typically what you'll do then is for service steps, you'll do integration downward into provisioning systems or whatever else systems in order to automate those actions to the greatest extent possible. Okay, so a lot of that really depends on the systems, again, that are underneath that take place. One comment, when we're instrumenting the network with this whole new stuff, there's a whole bunch more complexity here because, you know, I can have a compute failure that can impact multiple VNFs, and those VNFs could then cause a whole bunch of alarms and issues in your end-to-end services. And so you have to be able to sectionalize that. And so what's essential, and I haven't heard nearly enough industry dialogue around this, is how that has to be instrumented in order to ensure that you can actually sectionalize troubles and do analytics and such in a consistent and cohesive way on this whole new virtualized infrastructure. Similarly, you know, physical networks got deployed and then they realized that there was missing instrumentation that was required. That resulted in overlay probes and all kinds of things to help it. I think it's the right thing to do to actually do more thought around the whole virtual EPC, or the virtualization environment in terms of measuring performance. So that's the 5 easy steps. Those are typically being increasingly called a lifecycle service orchestrator. Now there are lots of different terms out there. This is the one we're attaching ourselves to, but I'm going to in a moment go through and show where that lies. So the last thing I'm just going to walk through is the industry context. Where does this fit? So everybody knows the existing ETSI NFV thing, right? The original. This is the original Mano orchestrator, which is VIM, VNFM, NFVI, VNFs, et cetera, and the NFV orchestrator that was in place. Now the blue stuff is stuff that is in scope of ETSI NFV ISG. Now, of course, there's this OSS BSS box, which the guy from Oracle, I thought, called it well when he said it was the box of fear. I have no idea what's inside there. I don't want to know. I don't want to change it. I can't change it, right? And we'll leave that to the TM forum. So we're not going to include that in the scope of ETSI NFV, which actually is the right thing to do if you're just trying to figure out the challenges of this first. But ultimately, this is talking into those existing physical networks that are taking place. So that's the starting point. There has been a very significant potential change that's underway. In fact, so the NFV, in IFA 09, there's now approved text to separate out the NFVO into the SODO portion, okay? And there's actually further discussion around an RO that fits down here, a resource orchestrator versus a domain orchestrator versus a service orchestrator. And I am strongly in favor of this. It's actually gained wide acceptance, why to split these two. And the reason is, there's actually multiple reasons. So the information model in a domain orchestrator is all about a particular NFV. How do you break that into components? Which virtual machines is that running on? How does that virtual machine map to your hardware, et cetera? So it's a very compute-centric information model that's required to perform that function. This is all about how end-to-end services across a multi-layer network cross combination of physical and virtual networks. So these are about services that cross. In addition, this scales differently depending on this. It's possible that you might have multiple service orchestrators for different service types talking to the same domain orchestrator. So for lots of reasons, this split is happening. The MEF is the one that's defining the lifecycle service orchestrator concept that's taking place primarily in the Service Operations Committee. And its role is to do orchestration across end-to-end services, again, sitting on top of the OSS BSS as I discussed earlier. But in addition, there's strong belief that a lot of the service orchestrator functions that are being separated out here would be combined into part of that lifecycle service orchestrator device. So, summary, services will cross combined physical and virtual networks for many years. You know, does anyone remember the TDM to Ethernet transition that we're still in? Now we're in TDM to Ethernet to virtual, and we're going to be in this for decades, if not years. Second, message NFV makes this very challenging and unsolved problem. Today, the way it takes a tremendous number of resources, people, time, etc., to assure today's network, to do capacity planning on that network, to understand the services across that network. And it makes this, the NFV is going to make this problem worse, not better, by default. The third is, there really are real-world solutions available to address this challenge. The ideas and technology have come from the world of big data, which is why I tied this to the Google Maps example, so you understand the kind of technology. And it's actually essential that, you know, when looking for lifecycle service orchestrator solutions that have this capabilities, that they are, that you're looking at the technology inside. If it's a standard relational database, you know, written in Java, 3-tier architecture, it might have some scaling problems when you try to do big data on it. You really have to be thinking about, you know, the Sparks and the Solar real-time searches and the Hadoop analytics and you know, the Cassandra rings, et cetera, the technology that is inside the big data solutions from the big over-the-top guys. The other key point here around lifecycle service orchestrators is it's unfortunate around this term because everyone, when they say orchestrator, thinks fulfillment. And so what happens is, the reason the MEF actually added the lifecycle on there is to say, well, a service has a whole lifecycle. It starts with its original design, it goes through fulfillment, but then the vast majority of its life actually is assuring it, keeping it up, measuring its SLAs, fixing it if it breaks, etc. And then finally it'll be disconnected at the end of its life. But the fact that lifecycle was added to the term, everybody still thinks it's fulfillment. So somehow, I'm not sure how this is going to play out, but I think more and more people are going to recognize that LSO really helps with the fulfillment side, but it also is actually critical in the assurance side of services. And the last thing about where this is being discussed, I think SDN hasn't much focus on this, both because they're not concerned with any of the physical networks that take place, but also they've drawn their boundaries that way that take place. More of the work is really going on relative. Also, if you go to the SDN and read the materials, there's still more about fulfillment. Everybody's still thinking about how to orchestrate it, meaning fulfill it, or how to instantiate VNFs, scale them up, scale them down, etc., which is kind of the equivalent of installing network elements in the virtual world, but it doesn't deal with the rest of the life cycle of services. So the work really going on this is LSO and MEF, and I think, you know, some of the special stuff is the ONF information models that are driven in ONF TMF MEF. So if any of you want to visit our booth and see an example of this, I encourage you to do so. I think we have a minute or two for questions.
Yes, we have time for one question. Question for Chris? All of you have no problems collecting all that information to update your inventory configuration management? One of the statistics we learned in our survey was that 67% of network performance problems and outages are due to configuration management issues. So implementing this architecture, even if you had nothing to do, even if you had nothing to do with NFV and SDN, is a very profitable, valuable thing to do. Would you agree, Chris?
Absolutely, yeah. And I mean, our real world big scale deployments are about physical networks, because there aren't any really big scale NFV deployments yet. But the key is, if you've done your information models right, extending that to NFV is actually a straightforward concept.
Just real fast, Tim DeWarin at ACG Research again. You know, I at least, I don't know about others, but tend to think of MEF as E-line and ELAN and those types of Ethernet-centric services. Here, we're talking about virtualization of all kinds of services, from VPN and IPVPN and other services. Is there any, I don't know, conflict is the right word, but is MEF the right organization, and are they thinking bigger than I just haven't followed MEF recently.
That's a great question. That's a great question. So, you know, if MEF actually is the one that defined what their initial coming out, you know, big thing that they did was defining Ethernet services and raising carrier Ethernet that took place. And you know, their MEF 10.3 spec was, you know, among the most important specs that's been produced in the industry. Probably a couple of years ago, people started recognizing that the #1 issue of Ethernet services was around the operation of those services, not the definition anymore. They'd solved that problem. And a service operation committee got formed, and it is extremely well attended by multiple operators, and it's now a big growing forum. So more and more focus of the MEF was all about service operations, not so much about the definition of carrier Ethernet services. And that has grown extensively in the last while when they recognized that with their whole vision of trying to do the third network of connectivity on demand and assured services on demand, they actually took up the challenge with that committee to stay focused on this. So that's really how the MEF grew to what it's doing now.
Great. Thanks, Chris. Thank you very much.